Hello, welcome. This is a new chapter of geometry. So welcome back, and it's going to be kind of a tricky thing because we are looking at two different textbooks that are somewhat parallel to each other. So there are going to be some theorems that are going to overlap, which is what we're going to be focusing on. And for the ones that will not overlap, well, there's just going to be more, I suppose. Arsenal for your artilleries then in this case. Okay, so let's go ahead and get into it. So the chapter that we're dealing with this time around will be dealing with circles. More specifically, circles with tangents and chords. And so we will get into what each one of those are and how do, what kind of special things you can actually do with those, okay? So the very first thing that we're going to look at, or we're going to define in this case, are tangent lines. So that is going to be our very first section. Well, actually, second section, because the first section was kind of introduction. So in terms of Moise, this is going to be 14.2, but in Jergensen, that is going to be 7.2. So to define what is a tangent line, well, here, let me just go ahead and write down the following different, show you the definition then. A tangent line is basically a line that touches the curve, in this case, a circle, right? And it doesn't always have to be a circle, locally at exactly one point. So then we have the following, which is a point of tangency. So the point of tangency is basically that point of intersection then, the intersection between the tangent line and also the curve. So here you can see the picture below, we actually have two scenarios then. In the left case, which is the one that we're going to most likely dealing with, will be the tangent line to the circle. So that means that we're going to touch the circle at that one single point that is over here. So you can see kind of like this right here, that's going to be my point of tangency. And let me go ahead and use red so you can see a little bit better. So right there, that's your point of tangency. But whereas for this tangent line, this is going to be its point of tangency. Now, the reason why I say locally is, well, if you look at this case of the curve right there, right, there are just like the circle, you have a whole bunch of different tangent lines. If I'm referring to locally, that means that for any tangent line, what I can do is I can go ahead and look at a small little box of where the tangent line and the curve is going to meet. And if I blow up that picture, you can see that that's what I mean by locally right here. So this is going to be locally, meaning, like in a small little window right there, you can see that this is going to be my point of tangency. And in fact, if you blow in far enough, one might even say that the tangent line looks almost identical to the curve itself because you're so close to each other. And even though that they're so close to each other, they're still going to intersect with each other only once. Now, the thing about curves is that when you look at a tangent line as a whole, sometimes the tangent line is going to cut or intersect with the curve at more than one point. So here's what I mean. For this tangent line right here, this one, you can see that it's definitely not going to touch the curve more than just that one point. But then for the one next to it, that's not going to touch the tangent line. Well, actually, this one it will, because if I extend the tangent line, you can see that that one is definitely going to cut or intersect with the curve at more than one point. So that's why I have to focus on locally, because when you look at that small little window, then you are only going to touch the curve only at that one single point. But in the case of a circle, you don't have to worry about that, because no matter where you draw the tangent line, you can see that it's always going to intersect the circle at only one single point. Now, here's the interesting thing that we are looking at for this section. When it comes to circles and tangent line, imagine, let's say that you have a tire. Okay, imagine that, let's say that you have a tire and you're going to have a road that it's on, right, for the tire. So here's the center of the circle. Let's go ahead and call that point P for the time being. What you'll notice that if I draw point P to the tangent line, you'll probably be able to see that, yeah, this right here is going to be perpendicular to the tangent line. So that is basically going to be our focus then for this section. So for any circle to where you draw the tangent line, I want to prove that it is going to be perpendicular to the tangent line at that point of tangency then. So there is basically what it looks like. I know one of them doesn't look exactly that good, but that's the idea then. Okay. Whereas for the curve, don't worry about that because that's just something else. Okay, so anyhow, that is going to be my first theorem right here, Theorem 7.1. This is, again, looking at Jergensen, the book, and I think it is a different theorem number in the Moise book, and I'll find it a little bit later on. I'm pretty sure it's chapter 14, I think like theorem like 14.2 or something like that. But anyhow, in terms of what it says is that if you have a line that is tangent to the circle, then the line that is perpendicular to the radius drawn to the point of tangency. So you can see here that O is going to be your center of the circle. P is going to be the point of tangency. And then that means that OP is going to be perpendicular. And you can see that little angle right there with a question mark to the tangent line. So that's what I want to prove. Okay, so in terms of the proof, here's what we're going to do then. We're going to go ahead and introduce a point P that is going to be on the tangent line such that Q is not equal to P. So that means somewhere on the tangent line, I'm going to go ahead and draw the point Q then, okay? So let me go ahead and do that. So here is going to be some point Q. Now it could be to the right, could be to the left, doesn't matter, it's up to you. Again, my focus is I want to show that angle P over there is going to be a right angle. Now, since we introduced that point Q, Q is a point that's going to be outside of the circle because it's on the tangent, right? So the tangent is located right here. Notice that the tangent anywhere else is going to be outside of the circle. And what that means is that QO, right, this length right here, is going to be larger than OP because if it's outside of the circle, then that means it has to be bigger than the radius. You can see that because for the radius right here, we know that this length right here is congruent to this length right here because it's the radius. So therefore, OQ is going to be bigger. And it doesn't matter where you draw this point Q, it's always going to be bigger than that. So then if we go back to a few chapters ago, there was something that was called the first minimum theorem that says that, hey, if any point on the tangent is going to be longer than this certain point, than this certain line segment that we have, then we can say that OP over there is going to be my right angle, meaning that the shortest distance from a point, right, to a line that external is going to be the perpendicular because anywhere else is always going to be bigger and so forth. So there it is. That's going to be my proof then for that theorem. So therefore, that point of tangency is going to be perpendicular. All right, so now let's go ahead and take a look at some of the special characteristics of these tangent lines that we can possibly encounter, and then some examples of problems that you'll run into. So first of all, I need to kind of define the following then. A line that is tangent to two coplanar circles is called a common tangent. So here you can see that we have a whole bunch of circles, and they are, I guess, like 4 different scenarios. And for each one of those, you will be able to see a common tangent. So for example, in this first case over here, where you have these 2 circles that are like, just away from each other, I can draw one tangent to one, and you'll notice that it could possibly then be a tangent to the other. So that right there is a common tangent. Now, if I go over here, I can probably draw the same thing, and you'll notice that that is going to be a common tangent then. Okay, so that is a case of a common tangent. Now, here's another one too. Maybe we can have the case where we have the common tangent up here, and then we can have the common tangent over here. So those are also common tangents then. In the case where the circles are intersecting each other, their common tangent is going to be at that point of tangency, which is located right here. And then for the last one, where if one circle is inside the other, where they are going to intersect at that point of tangency, then you can see that that common tangent is going to be over here then, okay? And there's something kind of interesting in the first case over here, which could be a theorem that we could actually prove. You'll notice that if I draw the center of the circle, right, I can claim that this right here, this segment from the point of tangency to the intersection right here is going to be congruent to this line segment at the other point of tangency. Okay, so you see where the question marks are. Those two, they definitely do look like they're congruent to each other. Now, if you're wondering how you can achieve that, well, here, maybe I can draw this for you, and you can follow up and finish up the proof. So here I'm going to draw the following, and we know that it's a point of tangency, and that means that these two right here are right angle, and this is congruent to this because they are radii. So see if you can figure out for yourself why those two are going to be congruent then. All right, so now let's go ahead and look at a given, let's say, example of a problem, okay? So this one is going to be a proof, so this one's going to be pretty lengthy, but, you know, I think we can handle it still. So in terms of what's given over here in the picture is that AB is going to be the diameter of the circle, okay? Then we're given that line I is tangent to the circle at point T, okay? And by the way, this little symbol right here, that means that your circle is going to be center with point P then, okay? So that means that your center is at point P, okay? All right, now let's go ahead and keep going. The next part says that AD is going to be perpendicular to I. BC is going to be perpendicular to I. And what I want to prove is that PD is equal to PC. So let's go ahead and maybe draw in some of the stuff so then that way you can see what's happening then. AB is this diameter. So that means that this length AP is going to be congruent to PB, that length, because diameter contains basically two radii then by definition. Let's see. We also know that AD is going to be perpendicular to I. So that means that we have a right angle right there. And then BC is perpendicular to I. So that means that we have a right angle right there. And we're given that let's see, we have line I is going to be tangent to the circle at T. So technically that means that we have some right angles right there too. So everything that's blue, we are extracting from the given. Finally, I want to prove that those two parts right there with the red question marks are going to be true. PD is equal to PC. Well, judging by the picture of what I have, I'm noticing that if I'm trying to show that PD is equal to PC, then I need to show by using the perpendicular bisector theorem the following, that PT is going to be perpendicular to I at T, and also DT is equal to CT. Because again, I'm going to try to use the perpendicular bisector theorem to show that those two segments, PD is going to be equal to PC. All right. Well, looking at what we have, we'll go ahead and break it into two parts. So the first part, I'm going to show that PT is going to be perpendicular to I. Well, that's not too bad because since I is supposed to be tangent to the circle with center of P at point T, then that means that PT is going to be perpendicular to I. And that's by using the theorem that we just came up with. So that's theorem 7.1. All right, next, afterwards, now I'm going to try to show that DT is equal to TC. Now, in this picture, the question is, how do I show that this part is equal to this part? Well, here, maybe I can draw the illustration underneath so you can see how this works out. So this is what it looks like with what we have. If I can somehow show that all those three lines are parallel to each other, then I can use the parallel proportionality segment theorem. Yes, there is a name to it. It's located in the Moise book at page 378 to say that dt is equal to dc. But anyhow, let's go through that one just to make sure. So first what I said was, since that AB is the diameter, then that means that PA is equal to PB, and that was by definition. Now, since AD is perpendicular to I, PT is perpendicular to I, and BC is perpendicular to I, all those three lines are perpendicular to I's. That means that those three lines, they must be parallel to each other. There was a theorem way back in chapter 9 that says that if two or more lines are perpendicular to the same line all on a plane, then that means that those lines are going to be parallel then. So we got the parallel part. Hey, that's basically the picture that we have right here. This is going to be parallel to this. It's going to be parallel to this. And remember, in the previous part, we just showed that AP is AP is equal to PB. So with all of those given, not given, but with all those that we just proved, that AP is equal to PB, and also the three lines are parallel to each other, then by that theorem, parallel proportional segment theorem, then we can say that DT over here is going to be equal to TC over here. So that's going to be the bottom part right there, okay? All right, so finally we can put it all together. Now that we know that PT is perpendicular to I at T, and T is going to be the midpoint of DC, because at this point right now, we show that this is going to be congruent to this, and we have the perpendicular at PT to DC. Then that means that by the perpendicular bisector theorem, this right here, PD, should be equal to this right here, PC. So that is going to be then my end of the proof then, okay? All right, so that one was definitely a little bit lengthy. I think some of the proofs that you're going to be doing will be a little bit easier than that, or a lot easier than that. Okay, let's look at this last one, which is going to be algebraic then, okay? Here we have three circles. What's given is that with the three circles that we have, they are all tangent to each other, okay? So they are all tangent to each other. So next, we are told that AB, which is the distance from one center to the other center, is equal to 10. Let me go ahead and write that in right now. Okay, so this length is going to be equal to 10. Then we also have AC, which is going to be equal to 14. So that's going to be this guy over here. And finally, BC is going to be equal to 18, which is going to be this guy over here. What I want to do is find the radius of each circle. Well, that seems, well, hopefully doable. The hint that we're given is that let one of the radius is equal to x. Well, let's go ahead and sneak that in there then, okay? So let's say that this guy over here is going to be x then, okay? So I'm going to go over to this part. Let me go ahead and denote that as x. Now, if that radius over there for that circle is x, then that means that this guy over here must be equal to x. Now, in terms of the other pieces, well, that's where the 10 and the 18 and 14 and so forth comes in. So here, the cutoff is that if that part over here is x, then this guy has to be 10 minus x then, okay? So let me kind of like just sneak that in so you can see it a little bit better, right? Because if the entire length is 10 and that radius is x, then this guy should be 10 minus x. All right, so if that's 10 minus x, I do believe that this is also going to be 10 minus x as well. And similarly, if I go over to the other side, since the entire length of BC is equal to 18, and since this part is equal to x, then this other part must be 18 minus x. Well, now for this last part over here, we have two options. Here, since this is 18 minus x, which is the radius of that circle, we'll see in it, then that means that this guy right here is also going to be 18 minus x. But then at the same time, we have to we can also utilize this 14 by saying the following. If 14 is the entire length over here, and this part over here is supposed to be 10 minus x, then that means that this part can also be expressed as 14 minus 10 minus x, which is also equivalent to this 18 minus x that I set up. And there you go. I think now we can solve for what x is equal to then. So 10 minus x in parentheses and 14 minus that is equal to 18 minus x. So we should be able to solve for x over here. That should give us 4 plus x in this case is equal to 18 minus x. So add x to both sides, we get 2x. Subtract 4 from both sides, we get 14. So it looks like x is equal to 7. And if we now go back to what we have, then we can finally plug everything in. If this length of x is equal to 7, then let me go ahead and replace that. Okay, so those are going to be 7. So this is going to be 7 over here. This is 7 over here. Then that means that these guys underneath, well, this 10 minus x would then be equal to 3. And then that means that this guy over here is then equal to 3. And finally, for the other part right here with the 18, if that's 7, then that means that this length has to be 11. And therefore, this last part over here has to be 11 as well. And notice now how everything matches up because it adds up to be 14 then. All right, well, there you go. Thank you so much for watching, and I will see you guys next time then. Okay, have a good one. Bye-bye.